Oh, we gotta go back. All right, write this again. Just kidding. Oh, wait, we better shut that door. Atkinson's getting on my nerves. That's going to be on the recording, dang it. Sorry, Christian. Okay, so the equation, 3x plus y equals 7. Normally, I just want to ask you a question. Normally, when I tell you to solve an equation, how many solutions are you normally looking for? One, right? If I asked you to solve a simple equation in your head, 3x equals 9. X equals 3, right? There's one solution to that equation. Well, that's because there's only one variable. This equation has two variables. So how many solutions does it have? 2. It does have 2. Does it have only 2? How many solutions does it really have? It has infinitely many solutions. If there's only one equation with 2 variables. Does the point 2, 1 satisfy? Yeah, it says it there. It's true because if you put in a 2 for x and a 1 for y, the sum of that equals 7. Okay? Rather than writing an infinite list of possible points that may satisfy that equation, what's a better way of representing the solutions to that equation? Anybody know? We need a way to show all of the solutions to that equation, every single one of them. A graph. Right? What is a graph? Some people really haven't made the connection to this yet, and it's such an important connection. What is a graph? It's a collection of points, you're right, but more importantly, it's a collection of solutions to the equation from which that graph was formed. Does that make sense? That's why we spend so much time graphing. I think, well, why do we graph? It's just a stupid picture. Well, what is the graph? It's a collection of solutions to the equation. If we were to graph this line, it's not so hard to graph, but what we would have is a collection of all the points that satisfy the equation. And not just integers, it would be all of the rational numbers, irrational numbers. Okay? So, I mean, they suggest here that you make a table of values. That only gives you a finite number of solutions, but at least it gives you a starting point of how to form the graph. And that's what they're talking about in this section. When they say you're going to graph functions, all you're going to have to do in this section of the book is plot a couple of points on a table, and then once you've got those, then you plot them on a graph and connect the points. Does that make sense? So you're not going to have to graph anything super complicated. They just want you to make a few points and connect those points on a graph. Seem okay? I don't want to spend too much time on this because it's pretty simple. Try this one. Real quick. Sketch the graph. Let's make a quick collection of points. I would suggest at least 5 so you can have a better representation. Whoa. Now wait a minute, this is second period, right? Okay. We get out 1040. Okay, we've got time. So I'm sure most of you are starting to construct a table of values. They do it horizontally. I don't know why. Most of us would probably do it as a vertical table. It doesn't matter. Does it matter what values of x you choose? Okay. In some cases it does, right? In this case, raise your hand if you're familiar with the concept of the domain. The domain. The domain means the set of all possible inputs, right? Or x values. The domain of a quadratic function is all real numbers. So in this case, it doesn't matter what values of x you choose. Just so you're aware of some of the terminology you might see on our tests or on the AP test, they might refer to this as independent and dependent variables. Have you ever heard that? The x is called the independent variable. Why is that?
you can pick whatever you want. But the y value is usually called the dependent variable because its value depends on what you've chosen for x. So it's an input-output or an independent-dependent relationship. Yeah. That's what, for this one. Just in this section. Yeah. If we're ever doing other graphing in other sections, there are other methods. I know it's going to take a little bit longer. It's just good practice. And then you connect the points for a parabola. Now, I know some of you are probably thinking, well, I remember this from pre-calc. The -2 just shifts the parabola down 2 units, right? Did anybody recognize that? That's okay. And that's okay to recognize. It was important, though, to get a few points on here. This is what's called a smooth curve. Smooth means connected. If it was just a collection of random points, that would be discrete. I think we can move on. We okay on plotting points and making graphs? Anybody have any questions on that? Make a table of values. Okay. I do want to clarify one thing, though. I don't know if I can write on. Let me see if I can write on this. What I mentioned before is, can you always just choose random values of x? What's the answer to that? Always for every function, can you just choose random values? Oh no. They're not letting me write on this. How do I go back? Let's see. Here we go. What if this were the function? You wouldn't want to choose x equals -2 or -1, right? So sometimes you have to be a little more careful on the set of domain points. So anyway, just be aware. So intercepts. And this is something we're going to see a lot of. X-intercepts and Y-intercepts. Okay? X-intercepts in particular are a little more useful in most situations. So starting with the X-intercept. How do you find the X-intercept? You let y equals 0. This is stuff you should have learned along the road in Algebra 2 or pre-calculus or college prep. Let me repeat that. How do you find the X-intercept of a function? You let y equal 0. Okay? How do you find a y-intercept? You let x equal 0. So it's pretty easy to find intercepts. Okay, depending on the difficulty of the equation, I guess. So to find x-intercepts, you let y be 0. To find the y-intercept, you let x be 0. This is just kind of an explanation of what we just said. Okay. Do all functions have both intercepts? No. You can see here this one has an x-intercept, no y-intercept. Sometimes the x-intercept and the y-intercept are the same. That happens all the time. And you might even be looking at things that aren't functions. The sideways parabola is not a function. Circle obviously is not a function. So just some things you'll need to be aware of for the homework. So just try it real quick. Let's just do a fast example 2. Find the x and y intercepts. One of these intercepts is much easier to find than the other, right? Let's maybe start with the easier one, and we can work on the harder one if we need to together as a class. Which one of those was easier to find, the x or the y-intercept? I would agree, the y-intercept a little bit easier to find. Who wants to Volunteer, come up to the board. Find the y-intercept for me. You want to write on the board? All right. Take that pen up there. Okay, good. You guys agree?
Yeah.
Okay, good. Now, we do need to start to be a little more accurate in the answer. You're absolutely right here. But an intercept is a point on a graph. You guys agree? So we need to represent this. Now, it's okay, because most students will stop here, and that's normal. But we need to start being a little more exact, because an intercept is a point on a graph. So what's the actual location of this point on the graph? 0, 0. Okay, so if you didn't write that, just write that 0. Does that make sense, Kate?
Yeah.
But you're absolutely right. It is 0. Now, exactly. Isn't this the origin? So this is one of the x-intercepts. I say one of them because there's another one. There's 2 x-intercepts here, but this also counts as one of the x-intercepts.
Now, finding the 2 x-intercepts was a little more challenging. So this was the y-intercept. To find the x-intercepts, what did we agree on? What do we have to do? Let y equals 0. And I'm going to go ahead and factor out an x. You guys okay with that? Now what about this thing here?
That's the difference of squares.
That's the difference of squares. This is a pre-calc thing here. There's actually 3 x-intercepts.
Because of the next.
Yep, this is a 3rd degree polynomial, which doesn't have to cross the x-axis 3 times, but at most it will cross it 3 times. So where do we go from here?
You've got to solve for 0.
Each one of these factors has to equal 0. Most students key and immediately align these two, but they forget this one. This is also a factor. It has 3 factors. Each one has to equal 0. So x equals 0, x minus 2 equals 0, and x plus 2 has to equal 0. This gives us the 3 x-intercepts. We have x equals 0, we have x equals 2, we have x equals negative 2. So the 3 x-intercepts are 0, 0, 2, 0, and negative 2, 0. Questions? Important thing to remember here, in addition to the arithmetic involved, the real important thing to remember is how do you find x-intercepts? And how do you find y-intercepts? You just got to remember. You let y equal 0, you let x equal 0. Okay? Oh, it's going to show us the solutions. Look at this. To find the x-intercepts, let's see if we got it right. Did we get it right? Woo! Wait, there it is, the x-intercepts. Okay, find y-intercepts. There we go. Hey, there's a picture of the graph. Do you recall having to graph these last year in pre-calc?
Yes.
Okay, one thing that we did not learn, though, at least maybe somebody didn't learn, you all should remember how to find the zeros, right?
Yeah.
We didn't learn exactly how high and how low these points, these turning points went. Remember, do you recall that?
Yeah.
This is something we actually learned in calculus. Exactly how high does this point go? And that's called the derivative. We're going to start to learn about that really early on, I think in the next couple of weeks, to find the minimums and the maximums. Okay? Other than just testing points, we're actually going to be able to find the exact values of them. So, next topic, symmetry. Matter of fact, you guys need to stand up. We've been sitting for too long. Everybody stand up for just a second. So, where were we? No. Intercepts, I got intercepts, finding its way. I got all that.
Was it recording during that whole thing?
No. Although I have done that before on accident. Symmetry, we're at symmetry. Okay, symmetry means same, and in relation to graphs, what do we talk about with symmetry? Same on both sides of primarily the y-axis. We don't tend to focus so much on symmetry over the x-axis. Can anybody tell me why? It wouldn't be a function. If something's the same on top and bottom over the x-axis, it doesn't pass a vertical line test. We don't tend to focus too much on that. But anyway, knowing the symmetry of a graph, you don't need to write this down, and it's not super important. But if you know a graph is symmetric to the y-axis, for example, all you got to do is grab one half of it and then reflect it on the other side, right? So, I mean, it's a method. It's not really widely used, but here we have a graph that's symmetric to the y-axis. As you can see, it's the same on both sides. It's a mirror image. Okay.
More important, though, is not just knowing the picture of the graph. What's the relationship between x and y values? Both the same y value for these 2 points, right? The x's are exact opposites of each other. That's an important relationship to try to remember. If it's symmetric to the y-axis, okay, whether you plug in a negative x or a positive x, what are you always going to get? The same y value. Okay? That's the important relationship there
For symmetry to the y-axis. We have a graph that's symmetric to the x-axis. They're not functions. Okay. And here we have a graph that's a little bit harder to spot the symmetry visually. That's called with respect to the origin, if it's symmetric to the origin.
But in terms of the coordinate points, that's an important relationship. Okay? Any point x comma y is reflected to its exact opposite, negative x comma negative y. That's how you spot a graph that's symmetric with respect to the origin.
Okay. So you do need to write these down. These are the tests
For symmetry, go ahead and write those down. Because you're going to have to figure out which functions are symmetric without looking at the graph here. Well, maybe a few of them with the graph, but that's too easy for you guys. You're going to have to find symmetry with just the equation of the function. So we did a little bit of this in pre-calc, so it might look familiar.
Hopefully it looks familiar. If you want to kind of shortcut this here, if it's symmetric to the y-axis, then x or negative x yield the same equation. So if I ever go through something too quickly, I haven't quite written it down, you can either say, hey, slow down, or you can also go back and rewatch it and fill in some things. Or it is in the textbook, that's true. But we kind of need to move this along here. So they want you to test this graph for symmetry with respect to the y-axis and to the origin. So let's take a look at this one here. We can't do both at the same time. Let's just work on one. So let's test. Whoa. Let's test y-axis symmetry. So y-axis symmetry. I have a slightly different way of writing this. I prefer function notation rather than this relationship notation here of x and y. So if we say that f of x is equal to 2x to the third minus x. So now we're using function notation. If f of negative x is equal to the exact same thing you started with, f of x, okay, then it's symmetric to the y-axis. That's what happens. If you plug in a negative x, but you get the exact same thing you started with, that's a test for symmetry on the y-axis. So let's see. If we replace all the x's here with negative x, do we end up with the exact same function that we started with? If so, then it is symmetric to the y-axis. If it's not exactly the same, then it's not symmetric to the y-axis.
So do we end up with the exact same thing?
So all I've done so far is replaced x's with negative x. This first term becomes negative 2x to the third. And then plus x. Compare that to what we started with. Obviously, they're not the same. So what does that mean? It's not symmetric to the y-axis. Not symmetric to y-axis. Now, if you want to test for symmetry to the origin, it's a similar thing. If f of negative x results in the exact opposite of what you started with, so if f of negative x equals the opposite of f of x, that means it's symmetric to the origin. So we already know what happens when we replace x with negative x. We end up with this expression right here, so I'm just going to drag this down here. So we have negative 2x to the third plus x. That's the expression we get when we substitute x with negative x. But what we have to determine is that the exact opposite of f of x. And sometimes it's a little hard to spot, especially if you have a bunch of terms. This only has 2 terms. I know for some of you this might seem like an unnecessary extra step, but I want you to do this anyway. Write it like this, please. It's a little bit easier to spot now if it is indeed the exact opposite. What did I just do there? Just factor out a negative.
Why would I do that? What do you notice is inside the parenthesis now? Inside the parenthesis is the exact function that we started with, and the minus in front means it's the opposite. This is the exact opposite of the function we started with.
What does that indicate? That it's symmetric to the origin. Symmetric to the origin. Because this right here is f of x. Inside the parenthesis, this is f of x. So we ended up with the opposite of f of x. So that's how I generally teach symmetry when it's a pre-calc course. They did a little bit different with x and y. I think function notation is a little more useful here. But solution y-axis symmetry, kind of hard to. So origin symmetry, let's see if we got it right. Simplify. Well, kind of went through that pretty quick. This is a picture of that graph.
Just by looking at the picture now, is this symmetric to the y-axis? Yeah. To the y-axis. Not to the y-axis, but is this symmetric to the origin? Here's you look at this one, 1, 1. Its exact opposite is down here, -1, -1. That's an indication of
a graph that's symmetric to the origin. Okay. Points of intersection. We've done this before. We're going to go through this real quick. I actually just showed you one when we were talking about that task.
If you have 2 equations that you're trying to solve as a system of equations, we solved it algebraically using elimination. What's another way to solve a system of equations? You could do substitution. Yeah, you're right. I'm thinking more graphically. We can graph both lines and see where they intersect. That would be a solution to a system of equations.
That's kind of what they're talking about here. You can find points of intersection of 2 graphs by solving their equations simultaneously as a system. Oh, let's start with a fun one.
Here's a system of equations. We're going to find all points of intersection not by grabbing, but using algebra. I understand it's been a while. Okay, both of you I think are on the same route. This is how I would recommend. Yeah, this is how I would recommend you visualize it. Rather than horizontal, let's look at these vertical. X squared minus y equals 3. X minus y equals 1. This was a topic in pre-calc. We have a quadratic function and a linear function. So just before we get too far into this, visualize this in your head. You have a parabola and a line. At most, how many solutions can we get? 2. Do we have to get 2? What if the line only touches the outer edge and is tangent to the parabola? How many points of intersection would there be? Just 1. What if the line doesn't even cross through the parabola? We get 0. So we don't have to find 2 solutions, but at most we will get 2. Many of you are suggesting the substitution method. That's probably the way I would do this. So, for example, if you add y to both sides, that becomes x equals 1 plus y. Now you take this value 1 plus y and substitute it right in there for x. So then that equation becomes quantity 1 plus y squared minus y is equal to 3. This isn't the only way to do it, but this is one way that it can be done. This is something you'll be doing soon. Looks fun, right? We got to simplify this quantity here, 1 plus y squared. It's okay if you make this mistake 1 time in this class, but it's not okay if you make this mistake 2 times in this class. Can you distribute that exponent? No, you cannot distribute that exponent. Okay? 1 plus y squared is not the same as 1 squared plus y squared. Those are unequal expressions. Okay? What do you do with it if you can't distribute the exponent? You can use the FOIL method. Okay? How the heck does a fly get in here? There is a little shortcut if you've ever been taught the shortcut. If it's a binomial, do you understand the word binomial? 2 terms. If you're squaring a binomial, the shortcut is to square the first term, so that's 1. And then you multiply these 2 terms and then double it. So that would be 2y. And then you square the last term. Just a little shortcut for squaring a binomial. Simplify here, we get y squared plus y plus 1 equals 3. Man, they're really taxing our brains now, aren't they? Now, how the heck do we solve this? I would subtract the 3. Is that what you're saying? Why not the 1? What's our goal here? Get it equal to 0, yeah, and solve it either hopefully by factoring. We're keeping our fingers crossed. If not, we'd have to use the fancy quadratic formula. Yeah, so come on, please. Does this factor? Does this factor? Does anything multiply to -2 that also adds to +1?
Yeah. -1, +2.
-1 and +2. So this factors into y minus 1, y plus 2. So the 2 values for y are y equals 1, y equals -2. Yep. So we were solving a system that includes both x and y. We have only found 2 y values, so now we need to find the corresponding x values. So when y equals 1 right here, you see where my mouse is pointing? If y is equal to 1 and you add a 1, what does x equal?
2.
So in that case, we have a solution 2, 1. But in the event that y equals -2, now you plug in -2 in for this y right here. If y equals -2,
Negative 2 plus 1 means that in this case, x would be negative 1. So your solutions would be negative 1 comma negative 2. Whew. Man, we need a break, right? Wow. Are your brains getting tired? Your muscles get tired after continuous use. What about your brains? Do they ever fatigue?
I think so.
That's why you sleep at night.
Just
Overuse. I've got an overuse injury.
I sprained my brain.
Yeah, it could happen. So it appears that two graphs have 2 points of intersections. It just goes through here. Let's see if we got it right. I always wonder if did we get it right? Let's see. Blah, blah, blah. 2 comma 1, negative 1 comma negative 2. Yeah. Okay, I'm going to let you guys go on this one with mathematical models. I did assign a few. I just kind of want to see how you, because the problem with trying to do some examples is the ones in your book are always different. So it's just, you'll say, well, these weren't like the ones in the example. It's just, mathematical modeling is something that you just have to feel comfortable starting, being unsure at times, maybe restarting, being confident. So let me show you where, man, we're ending early. Maybe I'll help you with a couple of the homework problems. So we're done with the lesson. Let me pause this. Let me show you where to find the homework problems. Say again? Yeah, you need to get the book from the book depository. I think she's there during school hours. Yeah, I think she's there.
Are we going to need to bring up one to class every time?